So we can finally take a look at the forward current of the PN junction to try to understand how it flows through the device. So in the previous video, we derived expressions for the diffusion current across the depletion region in terms of distance. And we found two special diffusion currents. The diffusion current of holes just as it is entering the N zone, and the diffusion current of electrons just as it is entering the P zone. These are Jp of xn and Jn of minus xp. We can now prove that the total current through the depletion region is actually the summation of Jp of xn and Jn of minus xp. Why that is so is because as holes are diffusing through the depletion region and electrons are diffusing through the depletion region, they do not get recombined. For recombination to happen, there have to be carriers. And depletion region is by definition devoid of carriers. Because there are no carriers, there is no recombination for any holes or electrons that diffuse through the depletion region. Which means basically that all the holes that are injected from the P zone get safely to the N zone, and therefore the current, the diffusion current, the whole diffusion current that just exits the depletion region into the N zone is the diffusion current of holes that has managed to get into the depletion zone. Similarly, we get electrons diffusing through the depletion zone, and the electrons that just managed to make it into the P zone are the electrons that managed to enter the depletion region from the N zone. This means that the levels of electrons and holes within the depletion region are constant, which we can see from these two graphs, and they are equal to P of xn and n of minus xp, which means that also the diffusion current within the depletion region is equal to the diffusion current at its borders, because the total diffusion current within the depletion region is constant. So holes are diffusing from the P side to the N side, leading to a current from the P side to the N side. Electrons are diffusing from the N side to the P side, leading to a current also from the P side to the N side, which means that the total current within the depletion region is the summation of the two current densities of holes and electrons diffusing in either direction. So this is going to be equal to Q into dP Pn naught over Ln plus Dn Np naught over Lp. And this is all going to be multiplied by e to the power of QVF by KT minus 1. So it's easy to see that this is the current density within the depletion zone. But the fact of the matter is, this is also the current density within the entire device. And this is a little bit harder to see. But in the steady state, the whole device is not going to have any accumulation of charges. So charges cannot remain at any location for a long time, which means that the total current flowing through anywhere in the device is going to be equal to the total current flowing anywhere else in the device, and it's going to be equal to the current flowing out of the device, which is I forward or I PN junction. And therefore, the PN junction current is finally A times Q times dP Pn naught over Ln plus Dn Np naught over Lp into e to the power of QVF by KT minus 1. A is the cross-section of the device. It's the cross-section of the PN junction. Now, this entire bracket is going to be given the term reverse saturation current, and it's going to be given the symbol I naught. So this is I naught into e to the power of QVF by KT minus 1. Why do we give it the name reverse saturation current? If you assume that the forward voltage applied is minus infinity, so it's actually reverse voltage, you'll find that there is a current that manages to flow, and it's equal to minus I naught. So I naught basically represents the maximum amount of current that flows in the reverse direction. In fact, if we try to draw the PN junction current against VF, we find that it increases exponentially in the forward direction, and that it saturates at a value minus I naught in the reverse direction. This is the asymmetric behavior of PN junctions that we have talked about before. Now, we have to understand what happens to the current, to the total current throughout the whole device. Particularly challenging is understanding what happens to current components as we get into the neutral zones. So basically within the depletion region, we have an electron and hole diffusion current. So we have an electron diffusion current and the hole diffusion current, and the summation of these two current components is then the total device current. As we enter into the neutral end zone, the hole diffusion current drops exponentially. And as we enter into the P neutral zone, the end diffusion current drops exponentially. The reason they drop is because carriers quickly recombine, and as they recombine, the gradient drops, and therefore the diffusion current drops. So at first glance, it might seem that the diffusion current is not important because it quickly dissipates on the other side. But we have already concluded that the total current of the device is actually the summation of these diffusion currents, because they are both intact within the depletion region. So what happens in the neutral zones? The total current has to remain constant within the neutral zones. So we have to have a total current that is equal to the summation of these two current components within the depletion region. So what happens in the end neutral zone is that as the whole diffusion current drops, we get an electron current that rises at the same rate. And at any point, we'll find that the summation of these two currents is equal to the total current, which is the summation of the two diffusion currents within the depletion region. And so also, this happens on the P side. As the whole diffusion current drops, the electron diffusion current rises, and we get a summation that is equal to the total current in the depletion zone, which is the total current in the device. So what are these currents? What are these majority currents? So what's happening basically on either side is that as the minority current drops and dies out, the majority current rises to replace it. So what is the nature of these majority currents? What is their nature? So these are diffusion currents. It's really wrong to think of them as anything other than diffusion currents. We can see that they are diffusion currents because when you look at the band diagram of a forward biased PN junction, you will find that in the neutral zones, the band diagram is pretty much flat, which means that there is no field in the neutral zones. Because there is no field, there's no drift. So these currents are by necessity diffusion currents. But what does happen physically? Why do they diffuse? What's happening here is that as we diffuse holes into the end zone, these holes are being recombined. But they recombine with electrons from the end side. And so what's happening is that the holes that recombine create a vacuum of electrons because they annihilate some electrons alongside them. This vacuum of electrons will attract electrons from the rest of the neutral zone, which moves the vacuum into the neutral zone, causing the vacuum to move towards the edge of the device. So we are seeing diffusion because we have created a gradient by annihilating some electrons. And this diffusion is going to propagate all the way down to the device until we reach the metal contact, at which point the electrons are going to be replaced from the metal. So these are both diffusion currents, and it is wrong to think of them as anything else. The main takeaways here is that the expression of the forward current is dependent on the forward bias, very strongly, exponentially in fact. There's a factor outside called the reverse saturation current, which when we look at it is almost entirely dependent on doping levels. And this is going to affect both the forward current and also the current that flows in the reverse direction. It's important to recall that the main phenomenon that allows forward current to flow in the PN junction is the diffusion of minorities across the depletion zone.